Okay, so we're not really doing much problem solving. Well, you can do problem solving within the theory, I guess. The goal is to prove this Muirhead inequality. So you remember we got started on this last time, right? And actually, the argument that we came up with was incorrect. Um, I don't know if you remember it, but basically, um, so one thing that we should probably keep note is that this doesn't work if it's cyclic instead of symmetric, okay? And basically, the argument we had was essentially proving that the cyclic sum works. All right, but I want to quickly remind you of rearrangement inequality. So this one's a nice one. It's one of those intuitive ones that, like, if you heard the intuition and didn't get the proof, you'd think that it was proved already. So it's just basically like if you have, um, like A1, A2 in like ascending order. You had X1. I'll do X, Y, Z and A, B, C. Okay, so if you have A, B, C and X, Y, Z, yeah, then and you were to kind of compose them, then the CZ plus BY plus AX gives you the biggest thing, and if you do it the other way, AZ plus BY plus CX gives you the smallest. So this is the max. This is the min. Okay. So and then all the other things like are in between. So like if you had like BX plus CY plus AZ, that would be in between those two. You know? That's called the rearrangement inequality. It's kind of obvious, right? It's just kind of saying like, yeah, if you have the most of the most thing, the second most of the second most thing, and the least of the least thing, that should be more than having um some other combination. All right, any questions about that? That's rearrangement inequality. Okay, so back to this Muirhead. So what does Muirhead say? It says that if you have a, a tuple of things here that majorizes something else, right? Then the symmetric sum. So we need these a's to be probably greater than 0. Well, we have that. It's greater than this symmetric sum. Yeah? Okay. And in the proof, we had that if we want to use AMGM, right? If we can prove like some weighted sum of the left-hand side terms is greater than or equal to just one of the terms on the right-hand side. So something like this. So if you get something like this, so like a weighted sum of the left-hand side is greater than or equal to just one term on the right-hand side, you can take the symmetric sum of both sides. Yeah. Okay. And what happens is this symmetric sum basically, yeah, I'll show you. So this symmetric sum, okay, so this symmetric sum, like, I guess the key is it's a symmetric sum of these variables, right? So it doesn't really care about the W, okay? So it goes inside to here, okay? And because it's a symmetric sum, it doesn't care about these sigma. You end up getting all of them anyway. So you can get rid of the sigma, okay? And then because there's no sigma, you can get it outside the sum, and um, and we know the weights add up to 1, right? Okay, so then we get the left-hand side. That makes sense? Okay, so basically that says that um, if the weights exist for us to do that, then we've solved the problem. Yeah? Okay, but the problem is showing that the weights exist wasn't as easy as we thought it was. Okay. Huh?
Spencer said he's still sick.
Oh, okay, that's fine. Okay, so the idea we had last week was we basically had a cyclic permutation of these terms, and we had n of them, and we just tried to restrict having weights for those, right? But that won't work because we can't prove it's true for cyclic sums. Okay. Okay. And then, okay, but then we also kind of forgot a few of the conditions on the weights. So let's just try to get weights on everything, yeah? Okay. So if we take a weighted sum of everything here, okay, we want the powers to match up to the right-hand side, yeah? So you get like expressions like this. So you need the weighted combination of these x things to add up to y1. Yeah? Does that make sense? And you want uh these other combinations to add up to yn. Um so if you're actually looking carefully, this is not exactly the same thing because we had if you're looking carefully, we had the sigmas on the ones here, yeah, on the subscripts of the a's. But now we got the sigmas on the subscripts of the powers, yeah. So what this really is really the inverse. Like if sigma goes here, then nothing goes there. Or like if sigma inverse 1 goes here, uh, then wait, if 1 goes here, then sigma 1 goes there. Yeah. And so in some sense it's the same. We're just summing the inverses instead of the sigmas. But they're the same thing overall, yeah? Okay, so not to worry too much about that. Basically, our condition for the weights existing is there exists these weights, one for each permutation, so the n factorial weights, yeah, such that when you sum them up with these x's, you get y1 all the way up to yn. Does that make sense? Okay, so I want to state this thing again, but instead of having n equations, I'll have one equation and have the y's all as one vector or one tuple, n tuple, yeah? Okay, so I need people to understand this statement first, because this statement is the key to what I'm gonna say. Oh, I should also mention, after I do this, Alex will also present an alternative approach to this proof. 他们都不来，就他们两个。
真的？
对，他们都在网上。Okay, so let me just state this thing again.
这讲什么？
组织 Okay, begin 0. So apparently this is called Birkhoff's theorem. Okay. So I might only state one direction now. If x1 xn majorizes, right?
Got a bracket.
Majorizes y1 yn, then there exists then for each permutation sigma in Sn, yeah, there exists W sigma greater than or equal to 0 with sum equals 1 such that sum sigma in Sn W sigma, and here we have, I don't know if I should use square brackets or curved brackets. It should actually be sigma, sorry. Is equal to y1, y2, yn.我可以吃方便面吗？你想吃方便面吗？ Do you want to eat instant noodles?
我随便。
给你烤点辣点，大概是不让。
你不用客气，
不用客气。
他真的是随便，因为你给他吃什么他都吃。
哎呀，
但是你可能不是很随便。
我随便吃什么，就不喜欢饺子。
我不喜欢饺子，你看听见了吗？
喜欢饺子。
不是那么随便的。Alright, is this the right statement I'm trying to do? You see the statement of Birkhoff's theorem is exactly what we need.
Oh. Yeah.
Yeah. It's just putting them all into one equation. Yeah. Okay, so the cool thing about this equation is it just looks so nice. Okay, so this, another way of saying this is like in an n-dimensional space, yeah, real space, if we take all the permutations of X and its convex hull, yeah, then then anything that X majorizes lies in that. You know? They will contain any Y that X majorizes. Okay. Do you guys know what convex hull is? So in like 2 dimensions, yeah, you just have a bunch of points. The convex hull is like, I mean, it's exactly all the combinations of all the points where the combinations add up to 1 and a positive. Yeah. So like if these are the points, if you take all the convex combinations, like you'll just basically get like the polygon. Does that make sense? Does that make sense? Or in like 3 dimensions, it'll be like a 3D polygon. Yeah, but you can't go outside. You can't go outside. Because then you need like a negative combination of these two. Okay, anyway. Okay, so there's a kind of a... So this is like the starting point behind what I want to say. And yeah, it just seems very nice. So basically, if we can prove this theorem, we can prove the Muir-Head. Yeah? Actually, we also can show you, we can also prove the Karamata as well. Okay. We can prove the Karamata is equivalent to Jensen's. Okay. So what's the idea behind this proof? I mean, there's probably, I don't know, I found a bunch of, there were a bunch of things I found, like I kept, for some reason I couldn't read them, but just from the names of the lemmas, it kind of gave me an idea of what it was trying to do, okay? So maybe we can do as an exercise together. So we can do as an exercise together. We can try to prove, we can turn the ideas into a proof. Okay. So the first claim, okay, is there's a linear function. Oh, Alex proved the Birkhoff. Yeah, actually, I'm looking for also a more elementary proof as well, but this is the proof I found. It's kind of nice as well. It gives me flashbacks to certain things. Okay, without further ado, the claim is like this: there's a linear function. So, how do you write a function? So you have a function. So it's a linear function on the n-dimensional space. Yeah. Let's say it looks like, so it's like z1, z2, zn. Okay. And it equals so some combination of the input ever. Yeah. Okay. And the claim is if you substitute the x's in, okay, so if you substitute the x's in, I guess, so if you substitute anything in the convex hull in, okay. Oh, sorry, I should mention also, okay, assume that because in our thing we have a y and the x. Assume for a contradiction the y is not in the convex hull, yeah? Assume this is not true, yeah? So assume that this yeah. So assume that y is majorized by x, but y is not in the convex hull, right? Okay. Yeah. So the claim is there's a function like of this form, okay? There exists f, yeah, of this form, such that f on any point in the convex hull is negative, okay? And f of y is positive. Does that make sense? Does the claim make sense logically? It probably doesn't make sense conceptually, but like,
How do you? Oh, it's Rn to R.
yeah.
Oh, yeah. That makes sense.
Does that make sense? So like, there's like a function that can tell the difference between them. Okay.
Yeah.
Yeah, and this gives me flashbacks because literally, okay, like I remember in year 12, extension 2, okay,
Yeah.
this was like the only question I couldn't solve. It was literally the only question I couldn't solve, and it was like, it basically involved. Do you guys know this formula for like if you have a point and a line, you get the distance, like the coordinate, the formula for the distance between a point and a line. It was something like if the line has equation like ax plus by plus c equals 0, right?
Yeah.
If that was like the equation of the line, then the distance was something like d equals, and this was like the point, like let's call it AB, yeah. Actually, sorry, no, not AB. That's bad, very bad, very bad. Minecraft data pack.
Why is my
Yeah, yeah. This is called like the separation theorem because it's kind of this thing can tell the difference between these two objects. You know what I'm saying? Okay, so it was basically like this. You have like, okay, call this point like UV, yeah? UV, yeah? Okay, and the distance formula was something like D equals the absolute value of AX plus BY plus C, but you have U and V here instead of X and Y, yeah? And you divide it by like the coefficients squared or something like this, yeah? Or something like that, okay? And basically the difference between me solving the problem and not solving the problems was the absolute value sign. Like I actually don't remember the actual problem, but I remember what the issues were. Like it was basically like, because with the absolute value sign, if you took certain points, like it was hard to combine the expressions or something, right? But what you're meant to do was you're meant to realize that like the points on like one side of the line had positive expression and the ones on the other side had negative expression. So you could remove the absolute value signs.
Yeah.
Does that make sense? You understand what I'm saying?
Yeah.
So basically the idea was if you understood the formula, which I didn't understand at the time, I was just mindlessly applying it, right? If you subbed in points on one side of the line, you got a positive expression. And if you subbed in points on the other side of the line, you got a negative expression.
Yeah.
And obviously if you subbed in points on the line, you got 0.
Yeah.
Right? And so yeah, so I missed that completely. But I got a lot of partials for using the formula. Anyway, but can you see how it's related to this? Okay, it's related to this because like this line is literally what separates stuff. Okay. So if you have two dimensions, right? Yeah. So you have like a convex, like a bunch of points, yeah? And in two dimensions you get this convex hull, yeah? That makes sense? Then like we're assuming the y is not in the convex hull, so it's like somewhere over here, right? Yeah. And so the idea is if this is not in the same hull as that, you can draw a line that separates them. Does that make sense?
Yeah.
And that line, okay, the equation of a line is ax plus b plus c equals 0, right? See what I'm saying? You understand what I'm saying?
Yeah.
So that's the function that we want, see?
Ah.
Because that function equals 0 on the line. It takes positive on one side and negative on the other side.
Yeah.
Does that make sense? Alright, are we all on the same page? Oh, f doesn't have constant term. What's happening? Oh, why doesn't f have constant term? Oh, maybe we need a constant term. Yeah. What's like the equation? Do you know the equation? We should probably do this for 3 dimensions. But like, obviously for 3 dimensions it's a plane, right? And if for n dimensions it's what's called a hyperplane. So hyperplane is supposed to have n minus 1 dimensions.
Yeah.
Yeah.
It's just your should be one.
Okay, so so if we do like 3 dimensions, we get like C1 it's kind of weird switching to XYZ or something. I think we're still just gonna have like Z1 plus a constant, yeah? Does that make sense?
Yeah.
Okay, so the next one now that we have like um we have a kind of a concrete expression, yeah? So we got like C plus C1 Y1 plus C2 Y2, yeah, plus C3 Y3. We got that's greater than any convex combination of the permutations of the x's. Yeah? So how would you say that? Uh, let's not say anything for now because kind of can't be bothered writing it right now. But like um okay, does that make sense? Alright. Now what I want to do is if we take instead of having oh, okay. Another thing is it's the other side is also plus C, right? There's plus C on both sides, so then you can cancel the plus C's. Yeah. So it's legitimately some combination of y's is greater than or equal to some combination of x's. Yeah.
Oh yeah, that's true.
Maybe I should write down what the combination of x's are. What is like a thing that's in there? Any I mean, it's also greater than the boundaries as well. Okay, I'll know what to write once I do the next thing. Okay, so if we reorder the C's, yeah, and call them D, okay, and then have D1 be the greatest. So order it like how the Y's are ordered, yeah?
Yeah.
D1 is greater than D2. That's just D3. Okay. So if we order this like this, then we want to show D1 Y1 plus D2 Y2 plus D3 Y3, yeah? We want to show that's greater than or equal to D1 X1 plus D2 X2 plus D3 X3. I could write that better.
Oh, and that's just
This is not the time.
rearrangement of right or something.
Okay, so by we know that if we order it like this, we know it's bigger than the C's, yeah?
Yeah.
You understand?
Yeah.
By rearrangement, yeah? Okay, and then hopefully we can write some expression here that looks like this, yeah?
Yeah.
Okay, so we want to prove this. So we want to prove.
Haven't we kind of already done that though? Actually did that Parramatta or weighted Parramatta. Right? Isn't there any? Because what we're here is with like multiplying two majorizing sequences, right?
Ooh.
Kind of already done it. But it should be the same as what we did. I think I remember argument we made for weighted Parramatta.
Really?
Yeah, because we made some like if you multiply the D3, like yeah, one sequence majorizes another.
Yeah.
And we multiply both. I mean, multiply each term in like the same order.
He's not wrong.
The majorizing sequence, bro.
Okay, he's wrong, but he's got a good idea. Okay. So
It's,
I think So okay, so the reason we want to prove this, right?
yeah.
Because I think it contradicts the thing that you're saying, and then we get the contradiction.
What is it?
Because I think the weighted Karamata goes the other way, doesn't it?
That's what I'm saying. But no, that's what I was saying.
Why you say it in that tone though?
Well, yeah, because that doesn't hold because we know that D3, D2, D1 majorize D3 to D1 definition of it, and X3, X2, X1 majorize Y3, Y2, Y1.
Speak up.
And then we already proved X3, D3, X2, D2, X1, D1. Well, we did something that should be equivalent to X3. Oh no, That's fine. It is Caramata. It is weighted Caramata.
Oh,
It's literally equivalent to the statement of weighted Caramata. Because x3, x2, x1, like f of x equals x is still a convex function, right? And yeah, we proved Caramata already.
so we don't need Karamata for the next part, but so what he's trying to say is, okay, so what I'm trying to say is the reason we want to prove this, okay, is because it contradicts um um it contradicts d1 x1 plus d2 x2 plus d3 x3 is greater than or equal to d1 y1 and you're saying you can, and Liam's saying you can prove this thing by Karamata.
Yeah. Because, like, Michael, because proving that, right, is equivalent to proving that the y's are in a convex hole. Is it not?
Alright, we're gonna take a small aside. What do you mean by proof? Can this can be proved by Karamata?
What's it called? It is equivalent to weighted Caramata. Because with you,
What are the weights? The D's?
these are the weights because it's a sequence which majorizes like d1, d2, d3, majorizes d1, d2, d3.
The functions like the identity functions, right?
Exactly, yeah. And then it is Caramata. That's true. Also,
Okay, that's kind of interesting. So,
Michael, the thing at the bottom that we want to prove, but
just one thing at a time, you understand? Don't be annoying. So, okay, maybe a reminder about Karamata. What is a statement of Karamata? So, a statement of Karamata is if we have a convex function f, we have a convex function f. So this is weighted Karamata. We have a convex function f. So this is the statement here. The weighted sum of the x's, and x majorizes y, then the weighted sum of the f of x's is greater than equal to the weighted sum of the f of y's. Yeah? But it's not just the x majorizes the y's. It's also that you need the wixi to majorize the wiyy. Okay. So yeah. Okay. I think that's quite nice that you saw that, yeah. Because we wanna so we know it does majorize it because like D, so we want I mean I think it's all divided by the sum or something, right?
yeah,
To make it properly weighted.
yeah.
I guess you don't even need the weights to add up to 1.
No. Like for weighted,
Oh wait, you might.
no. Just
Oh, it's the same weights on both sides.
this is the way.
Okay, anyway, so for the weighted Karamata thing, Because we know d1 x1 is greater than or equal to d1 y1, right? And we also know that d1 x1 plus d2 x2 is greater than or equal to d1 y1 plus d2 y2 by
I don't think I'm not actually.
Wait, I think we can show that by rearrangement or something.
Yeah.
Wait.
It's not exactly rearrangement.
What is this?
Ones and y ones are like, oh,
d1 x1 plus d2 x2. Is it obvious that it's greater than or equal to d1 y1 plus d2 y2? Wait, that's confusing because then you get d1 x1 plus d2 x2 plus d3 x3 is equal to the other one. Do you? But that's just like that's just the inequality in the first place.
yeah, no, you did. The Caramelic
Okay, so maybe we don't quite have the Caramata thing, yeah?
Oh wait, no, I think we might actually. Yeah. It's not Caramelic, we did rearrange it. We can view like we know x1 plus x2 plus x3. Actually,
Yeah, there's some okay. So we can actually prove this with some kind of nice telescoping argument, I think.
yeah.
How do we do that?
We get
Alex also thinking this.
yeah.
Okay, let me think. So
Oh yeah. Well, I think I have an idea.
so d1, then it's like can you do it? So d2 with d1 x1 minus y1 plus d2, and then we want something like x1 plus x2 minus y1
I
minus
don't
y2.
think you even need to do that.
Huh?
I don't think you even need to actually do that.
Do what?
What we're doing, I think you can just do like b1 plus x1 minus y1, d2, and then you can like oh, it's like yeah.
Oh, so you get d1 plus d2 here, right? Or minus d2. Oh yeah, does that make sense?
Yeah.
And then you get d3 x1 plus x2 plus x3 minus y1 minus y2 minus y3. Yeah?
And then you take away d2, d2,
And that gives you
minus
minus
d2.
d3 here, yeah?
Yeah.
that make sense? Yeah, right. D on X1. Yeah, exactly. I think I might steal that right away. I'm gonna steal that Alex chat right away. And just write it down here. So some D X is greater than or equal to some D I Y I. Okay. Alright. Stole straight from chat into the proof.
I think that's what's right. So that's one.
Oh, did I not do the Y's? Oh. Oh, sorry, yeah. It's like that, yeah. Alright, we're all following. So this thing we know is true just from a basic one calculation, yeah? If x majorizes y, then if we times it by a decreasing sequence, it also is bigger, yeah? Okay. So now we just need to prove this thing here. Yeah. Okay, so let me just erase this. What is the 3 here? D3, X3. What is D1? Okay, so so how do we prove the other one? Oh, sorry, we're proving it's strictly less than, okay? That's a contradiction, yeah? Okay, so we're meant to do some kind of thing like this. So we get this thing here, right? It's greater than or equal to this rearrangement, yeah? And then something in this convex hull is meant to look like this expression. Yeah?
Meant to look like that expression. Oh, wait. Yeah, so what we give is the functions like C1, C2, Cn, right?
Yeah.
Yeah, don't you weight it? Like, yeah. You can choose the weight, so that's true. Because on
Yeah.
the weight, you choose the weight, because you can choose, you can choose the weight, so that's C1, W1, to
Like, we probably want it at the boundary anyway, you know?
yeah. So we know we can choose the weights to get us that decreasing sequence. We know we can choose W1 such that W1 C1 is equal to D1. You may not choose the
Like, for example, what is something that's on this? Like, in the convex hull is something of the form, like, it could be like x, like, sigma 1, right? x sigma 2, x sigma 3, yeah? That's something, that's one of the points in the convex hull, right?
Yeah.
Does that make sense? So like, so one of the things that it's bigger than is like C1, what do you call it? Like C1 x sigma 1, yeah? Plus C2 x sigma 2 plus C3 x sigma 3, yeah? Do you know what I'm saying?
You don't get them in the function directly because you can't necessarily use the weights like that.
What do you mean the weights?
Like, because you go.
No, that's one of the points. You don't need, like, it's a trivial weight.
Oh, yeah.
It's just 1, 0, 0.
Oh, yeah.
Let me draw that again. So it's like C1 x sigma 1 plus C2 x sigma 2 plus C3, C3, oh my gosh, x sigma 3, yeah? You see? So like, the function outputs a negative number for everything
Oh, yeah.
of that form, yeah? So over all the different sigmas, yeah? So can you see that this expression is bigger than this expression? So that's what we're trying to show, right?
Yeah.
Oh wait, are we trying to show?
We're trying to show that that expression is smaller than the y expression, right?
Alright, sorry, we're trying to show this
It's equal to.
yeah.
Yeah. If you
Okay.
have to choose the output, but or we could choose the expression.
Yeah, so this expression is greater than everything of this form, yeah? And when this is something of that form.
Yeah. No, that's not what you're trying to show, so. Yeah, that's like,
What do you mean?
you're trying to show that that expression is something of that form.
Isn't that what I said just then?
You said it's greater than everything.
No. This expression here
Yeah.
is greater than everything of this form,
Yeah.
right? And this
Oh.
expression is something of this form.
So, yes, right.
So then it's greater than this.
Yeah.
Yeah, I guess this expression also happens to be the biggest thing of this form as well.
Yeah.
Is that true? Do people agree? Oh, Alex, confusion. Alright, I might start typing this up as we relieve confusion. What is which part confusion? Oh, the C's are not ordered, so the C is just some random ordering. The D's are ordered. The D's are just the C's reordered. All right, so what's all right, maybe I should type this up. Okay. So we want to show there exists D one D. So sum of dixi is less than sum of diyii. Contradicts lemma.
是你的。
No, I'm gonna erase this. Can I erase this? I should probably type it again. Okay, let me type it again. Oh, there's actually one slight issue. Do you see it right now? It just as I'm typing this. You can't see anything?
It's just hard to read because it's like text and text.
Okay. But I'll erase the stuff that I've typed, okay? So we typed this. We typed this. Mhm. Okay. So D greater than or equal to let DI be in descending order. C1 Y1 plus C2 Y2 C3. Alright, we're gonna start our transition at dinner soon. Y3, and then it's this is greater than C1 X plus C2 X 2 C3 X sigma 3 for all sigma, which is greater than or equal to D1 X1 plus D2 X2 plus D3 X3. Alright. Alright, let's have a look at this. Yeah, so here if we have D1. Alright, so the D's are decreasing, yeah? And X majorizes Y. X majorizes Y. Then the the sum of the DIXI is greater than equal to the sum of the DYIYs, yeah? DIYIs, yes? Okay, and it's like a nice telescoping proof. Okay, and then we're trying to show that if Birkhoff's theorem is not true, then we can contradict this lemma. Yeah? Okay, so if Birkhoff's theorem is not true, we can construct DIXI to be less than DIYI. Yeah?
Yeah.
Yeah, so if the Y is separate from the convex hull, then there's essentially a linear function that separates Y from the convex hull. Yeah? So it's positive on the Y and it's negative on everything in the convex hull. Okay. And so if we take the so the function has the constant CI's, yeah? If we rearrange them to DI's in decreasing order, in descending order, then the DIYI's is bigger than the CIYI's, yeah? Okay, but then the CIYI is bigger than the function evaluated at anything in the convex hull. So in particular, anything on the like the boundary, the initial points that generated the convex hull. Yeah. Okay, and then we can take the permutation for all the permutations, but we can take the permutation to be the one that matches, like whichever one's the D1, it matches the X1 to the D1. Yeah. Does that make sense?
Yeah.
Alright, see if Alex still confusion.
Why did you change color?
Oh. It's the orange Alex was confusion, but the purple Alex is not confusion.
Why is Alex now cyan?
Alright, does that make sense? So actually, something I was hoping maybe Liam might notice is like having his Zoom keeps crashing. Having a function that's like having a plane that separates the two things, right?
Yeah.
That's one of those things that's intuitively obvious, yeah?
Yeah.
But there's a difference between that and a proof of that. You understand? So like if you actually try to prove it, it's not as trivial as you might think.
Yeah.
Because in your mind, it's like a convex thing is like this,
Yeah.
right? And a point is like that, and you can always find a plane in between, right?
Yeah.
But
What if it's like funny?
no,
I mean, I feel like you can just take like the planes at the faces of the convex shape, right? And if it's inside, in the correct side of every single one of those planes, it has to be inside the convex shape. Like one of those planes has to separate it. Because it's defined as like the like Michael, is it like correct to think of like a convex shape as the intersection of some sides of a number of different planes within three-dimensional space?
actually, that's a pretty good idea.
And
Yeah.
that kind of does it instantly because if it's inside all those planes, it has to be inside the convex shape. And it's not inside the convex shape because it can't be inside all those planes. One of those planes separates.
You can translate one of the planes.
Yeah.
Okay, well-definedness of the convex hull in the first place isn't the easiest thing, yeah. Yeah. So there's definitely lots of issues, but at least now it's kind of believable. And Liam's idea isn't actually too bad. It's like if you have a plane on the boundary of the convex hull with the point on the other side, you can kind of move it so that it's somewhere in between.
Yeah. And there has to be like some.
Yeah.
Yeah.
I think certainly at the level of high school, saying that is like almost more than a proof for most people.
Yeah.
Yeah, you would need to claim that you would make everything
That's
inside the convex hull. Yeah.
Is sure.
Yeah, there's definitely some issues. Yeah. Yeah, because we're only thinking of the stuff as everything inside, but we haven't proven it or anything like this.
Yeah.
他们为什么不来？是因为饭不好吃吗？
不是啊，不知道。
哎呦，打你了，
Alright, so
然后洗手了，好，去拿你的面粉。啊，你的你也有，你也有。
what was I gonna say? I was gonna say something.
原来你要吃 hash brown 吗？我拿一个给你，我拿一点点尝一下，好不好吃？
啊，你还煮 hash brown，浪都不来。
不来就不来啊，明天儿子吃。
嗯。
我已经拿出来解冻了，知道吧？
啊，好。Okay, so let me just think what I want to say. I want to say, okay, so from Burkhoff, yeah, I guess a lot more can be said about the convex. There's actually a lot of issues here, and so, and then yeah, Alex will talk about this again, maybe a different approach after dinner. One thing I want to mention just before everyone tunes out is there's a nice so from Burkhoff, like because what we have from Burkhoff is we have like a weighted sum of like x sigma 1 or something equals by 1, right? That's what we get from the Burkhoff, right? And we get it for all of the okay. If we take a convex function f, okay, and we take f of both sides, we get f of y1 equals f of this. You see?
Yeah.
And if the f is convex, right? If f is convex, we know from the weighted Jensen inequality, yeah? We know from the weighted Jensen inequality this is greater than or equal to or is it less than or equal to? It's less than or equal to, sorry. It's less than or equal to yeah. You see? So this is less than or equal to.
太不晕，我转几圈我就晕了。
That's weighted Jensen, right? This is weighted. Okay, okay, does this make sense? So then if you add them all up,
是啊，
if you add them all up, you get sigma W sigma f of x sigma 1 plus f of x sigma 2 is greater than or equal to f of 1 y1 plus dot 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 plus yn. Yeah?
我脑袋里插进去。
Wait, does that make sense?
停，他疯了，对，兴奋了就这样。
Do you guys see this? Is this true?
No more.
Damn. You see that?
Yeah.
No more.
So you just add all of these.
不吃了。
Yeah?
Yeah.
Okay. But then like these are just a reordering of f of x1 plus f of xn, right? Yeah? Hello? And then this thing here is just 1. Yeah?
Yeah.
So do you see that proves Karamata? I didn't prove weighted Karamata. Maybe we need to weight this. Oh, but then you don't know what weight goes with which one. Okay. Alright, so we transition to dinner, okay? After dinner, Alex will talk about his findings with Muirhead. Wait, you guys have any questions about this?
Oh, maybe?
How was that surprising?
Oh, everyone's dead. What the hell?